Hey everyone, welcome to the next exciting lecture, because we're going to be exciting electrons in Chem 1111. Dr. Carroll here, and I'm looking forward to this topic. We are in our textbook, page 184, and you want to have your PowerPoint ready as well. And we've been looking at photons and photons being absorbed by atoms to excite electrons to higher energy levels. You get absorption spectra. The more common data we look at is emission spectra, when those electrons, which don't want to stay in excited states very long, fall down to lower energy levels and eventually to the ground state. And all sorts of stuff is happening at once. Let's look a little bit at the fact that electrons, like photons, have particle-like and wave-like properties. In fact, everyone has particle and wave-like properties. Even us, as humans, we have wave-like properties. There's waves associated with us. It's just we're so massive compared to electrons that there's no way we can distinguish it. But in a electron, you can see it. And so let's first look at properties shared by all electrons. They all have the same mass and charge. Mass, and I'm going to just write it on a piece of paper so I remember, 9.109 by 10 to the minus 31 kilograms. And they all have a negative charge of 1.602 by 10 to the minus 19 coulombs. They behave like tiny magnets. And the magnetic properties come from spin, which we're going to talk about, if not this class, then the next one, because you can think of electrons spinning in one direction, and it's associated with the magnetic quantum number, and the value is +1/2, or spin in the opposite direction, and then the value for the spin quantum number, m sub s, is -1/2. So only two different ways for each electron. Iron and nickel are permanent magnets because of the cooperative effects of many electrons. Wave properties. Louis de Broglie was one who discovered that for electrons. If you think of waves having you think of light having wave-particle duality, you think of electrons having them as well. And you can show, I'm just going to go right down to the proof in the pudding here, the wavelength of a particle. I'm going to get my highlighter here. Any particle has a wavelength equaling to Planck's constant over mass times velocity. Mass times velocity, some of you think of as momentum. Don't confuse speed with frequency. Okay, fine. I'll try not to. So lambda is h over mv. So that should be a v. This is speed, right? Why do they write it as frequency? They say don't confuse it, and they confused it. They meaning the textbook writers. Okay, so lambda of the particle is h over mv. And so how does that all work? You see right away, and if any particle, whether it's electron or anything else, has a wavelength, h is 6.63 by 10 to the minus 34, then you have a mass and you have a velocity. Well, unless the mass is really small, lambda is not going to be observable, right? If I'm 100 kilograms, well, already there, I'm going at 10 meters per second if I'm super fast, so that's 1,000. So that's still going to be a super small value for the wavelength of a particle. But electrons, 9.11 by 10 to the minus 31, so that is close. And if the electron's going really fast, then I can calculate the wavelength for an electron. Okay, then de Broglie talked about various patterns, intensity patterns, to talk about wavelengths, and scanning tunneling microscopes can give you information. So that's all good. We'll do a calculation in a minute. Let's just hear a nice summary, table 4.1. Equations for photons and for free electrons. We're talking about energy. The photon equation, which we've looked at, is E equals h nu. That's frequency nu. For electrons, well, if we're talking about a free electron, no potential energy, it would just be kinetic energy. The kinetic energy would be 1/2 mv squared. The wavelength for a photon, hc over E, right? E equals hc over lambda, so lambda is hc over E. And for a electron, lambda is h over mv. Okay? We just looked at this as velocity. Speed of any photon is 3 by 10 to the 8th meters per second. Here, it would just be isolating for the kinetic energy, so the square root of 2e over m. So those are the differences. Now, let's put it together. Here we go. The structure of a crystal can be studied by observing the wave interference patterns. This is example 4.8. I'm on page 185. The wave interference patterns that result from passing particle waves through a crystal lattice. To generate a lattice is an arrangement of particles. We're going to get to that later in this course. To generate well-defined interference patterns, the wavelengths of the particle wave must be about the same as the distance between the atomic nuclei. We want to have a good interaction between them. In a typical crystal, this distance is 0.25 nanometers, or 0.25 by 10 to the minus 9 meters. Determine the energy of a photon with this wavelength and of an electron with this wavelength. Okay, so for the photon, energy would be h nu or hc over lambda, right? So for the photon, hc over lambda, 6.63 by 10 to the minus 34 times 3 by 10 to the 8th over lambda, 0.25 by 10 to the minus 9. So punching that out, 6.63 by 10 to the 34 minus times 3 by 10 to the 8th divided by 0.25 by 10 to the negative 9, 7.96 by 10 to the minus 16. And that's going to be joules. Okay. And let me check on the next page here. Yeah, good. And then for the energy associated with the electron. Okay, energy for the electron. Energy would be 1/2 mv squared. And how do I get the v? Well, I got lambda equals h over mv, right? So v equals h over m lambda. So the speed of the particle, if I know its wavelength, so h is 6.63 by 10 to the minus 34, mass of the electron, 9.1 by 10 to the minus 31. I wasn't looking at the book. Sometimes I like just doing it without looking at the book, and then my thought process is I try to think aloud and hopefully model various ways to do these. You might just put on the mute button. Okay, so the speed is going to be, and just look at the number, 6.63 by 10 to the 34 minus divided by 9.1 by 10 to the 31 minus times 0.25 by 10 to the negative 9, and I get 2.91 by 10 to the 6th. Okay, so that is the speed, and once I got the speed, then the kinetic energy is 1/2 mv squared. So 1/2 times the mass of the electron, 9.1 by 10 to the minus 31, times the speed, 2.91 by 10 to the 6th squared. And I get 3.9 by 10 to the minus 18 joules. Okay. And going through, and yeah, it's all good. So the photon energy is 7.9 by 10 to the minus 16. The electron energy is smaller, 3.9 by 10 to the minus 18. Photon has a much higher energy than visible light, which is reasonable for X-rays. In fact, this getting the crystal information is usually called X-ray crystallography. The speed of the electron is about 1% of the speed of light, very fast, but not out of the realm of possibility. Okay, practice 4.8. In a photoelectric experiment, a photon with energy of 1.25 by 10 to the minus 18 joules is absorbed, causing ejection of an electron with a kinetic energy of 2.5 by 10 to the minus 19 joules. Calculate the wavelengths associated with each particle. Yeah, we can do that for practice. So the photon's energy is 1.25 by 10 to the minus 18. So that's E equals hc over lambda. So lambda is hc over E. And let's just punch it out here. So 6.63 by 10 to the 34 minus times 3 by 10 to the 8th divided by 1.25 by 10 to the negative 18. 1.59 by 10 to the minus 7 meters. So that's the photon. The electron which is ejected, kinetic energy is given. So can I relate kinetic energy directly to wavelength? No, I have to get the speed first and then I can get the wavelength. So the speed for the electron is the square root of 2 ek over m. So 2, what's the kinetic energy of the ejected electron? 2.5 by 10 to the minus 19 over the mass of the electron, 9.1 by 10 to the minus 31, 2 ek over m. So 2 times 2.5 by 10 to 19 minus divided by 9.1 by 10 to 31 minus, take the square root of that, 7.41 by 10 to the 5 meters per second. So that is my speed, and then my wavelength, lambda, is h over mv. So it's 6.63 by 10 to the 34 minus divided by the mass of the electron, 9.1 by 10 to the negative 31, times the speed, 7.41 by 10 to the 5. And I get 9.8 by 10 to the minus 10 meters. Okay, now let's check. I didn't check that one. This is example 4.8, practice exercise. 159 nanometers and 0.98 nanometers. Yeah, so that's good. Okay, wave properties of subatomic particles, electrons, neutrons, protons play important roles in the behavior, but other particles don't. And this question here, I'll just very quickly show you. Matter waves, if I want to get the electron, example 4.9, there it is, h over mv. So you get 7.27 by 10 to the minus 9 meters, okay, which can be interacting in spectroscopy with electromagnetic radiation. Ping pong ball, 11 grams. There it is. Convert that to kilograms, fine. 2.5 meters per second. I mean, all the stuff in the denominator is so much larger than Planck's constant that you get a much smaller value. This is interesting. They gave Planck's constant here, kilogram meters squared per second. You don't usually see it like that. When I think of Planck's constant, I think of joules per second. Now I know a joule is a kilogram meter squared per second squared. Multiplied by second, yeah, it becomes kilogram meter squared per second. Okay, yeah, that's another unit for that. And you can try the practice exercise 4.9 on your own. It'll just be lambda is h over mv, where you'd have the mass of the proton, so you would look that up. And I think in the textbook on the very first page, or the very last page, do we get a table with all sorts of things here? index of equations on the very last page. Oh yeah, we got some properties there on the very last page, back cover. Proton 1.67 by 10 to minus 27 kilograms. Now, speaking about speeds, masses, we talk about momenta, and it turns out that because electrons have these wave-like properties, you can't pinpoint where the electron is. This is famous principle. You've heard of it before, Heisenberg's uncertainty principle. There's all these jokes about it. Heisenberg was a famous scientist. Yeah, I know, the guy in Breaking Bad calls himself Heisenberg. But for our purposes, the whole idea is that you cannot know the position and momentum of a subatomic particle like an electron to a very high level of certainty. There is an uncertainty associated with that. It leads to probabilistic determinations in quantum theory. So this is known as the uncertainty principle. It's a feature of all objects, but it becomes noticeable only for very small objects. And it turns out that the uncertainty in the measurement, we aren't going to do the numerical calculations for this, just the qualitative idea, but it's saying the uncertainty in the measurement of the position of an electron times the uncertainty in the measurement of momentum is always greater than or equal to h over 4 pi. It just means that if the closer you are to knowing where the atom is, the harder it is to know what its momentum is. And it's never possible to predict with certainty exactly what will occur next. You can't measure it exactly if the universe is subject to uncertainty. So when we talk about electrons, protons, and neutrons, we're going to talk about that. And let's do that right now here. You can do the section exercises on your own. Okay, so we're going to get into the world now of quantum numbers and quantization. And here we go. Okay, so this is on page 188. Just before we start, is there anything in our slides which will help? Properties of electrons, that's that table we had, the example. Heisenberg uncertainty principle. The more accurately we know position, the more uncertain we're about motion, momentum. Probable location of the electrons in an atom, not an exact one. Okay, so now we're going to get into quantum numbers. So let me go here. So the allowable quantum numbers of electrons actually determine the arrangement of elements in the periodic table. Quantum numbers, there's lots of them. But in terms of electrons in atoms, we're going to be looking at a set of quantum numbers. I'll use the curly brace for set symbol, N, L, M sub L, and M sub S. So that is the series of indices for quantum numbers. The properties of electrons described so far apply to all electrons. Electrons traveling freely in space are bound to all these characteristics. Bound to atoms have these characteristics. Bound electrons have additional important properties related to their energy and their shape. Only certain specific values, those are quantized values. We start with energy, and there's only certain permitted values for a bound electron. Free electrons can have any one. Those bound values come from the solution to an equation called the Schrödinger equation, which describes the kinetic and potential energies of the atom. And in a few years you will take courses, if you go on in chemistry, where you will find ways to accurately and approximately solve the Schrödinger wave equation. And some of you from the Big Bang Theory have heard about Schrödinger's cat and all that interesting popular stuff. We won't talk about Schrödinger's cat today. Schrödinger equation has solutions only for specific energy values. I mean, if you really want, what you write here is you have something called a Hamiltonian, which acts on an orbital given the symbol Greek letter psi, which gives you energies times those Greek letters psi. And the energies are only certain allowed values associated with the quantum numbers n, l, and m sub l. And then m sub s comes a little later. So in terms of energy, the principal quantum number n is going to give us information about energy. The principal quantum number L is going to give us information about the shape of the orbital. The principal, why did I keep saying principal quantum number? N is called the principal quantum number. It gives you the energy. L is called the angular momentum quantum number, sometimes called azimuthal quantum number, and it gives you the shape of the orbital. M sub L is called the magnetic quantum number, and it gives you the orientation. And M sub S is called the spin quantum number. It tells you if the electrons spin up or spin down. Okay, so the solutions are called orbitals, and the orbitals have different energies and different shapes, depending what they are. So there's indices which put it all together. Okay, so describe an electron, you have to give these 4 numbers. So let's start with the principal quantum number, lowercase n. This I've already talked about as the energy quantum number. So n can have the value 1, 2, 3, 4, 5, etc. And the larger the value of n, the larger the orbital. So if we're talking about an s orbital, which some of you will remember from last year, spherical in its outer surface, so the n equals 2 s orbital is a larger, bigger than the n equals 1. Okay? Each successively higher value of n describes a least stable energy state. So if I go to n equals 3, that's larger still. Okay. This other stuff not so useful. Azimuthal quantum number, which I said is also known as angular momentum quantum number. This gives you the shapes of the atomic orbitals, and this is given the letter lowercase l. Okay, and the value of L correlates with the number of preferred axes in a particular orbital. And so you have restricted shapes, and they're linked to the energy, so they aren't totally independent. They're dependent on the n value. The smaller n is, the more compact the orbital and the more restricted its possible shapes. Historically, orbital shapes have been identified with letters rather than numbers, so it's like a secret code here. These letter designations correspond to the values of L as follows. So you have a value of L is 0, then you're talking about an s orbital. Value is 1, it's a p orbital. Value of L is 2, it's a d orbital. Value of L is 3, it's an f orbital. Scientists assigned the words sharp, principal, diffuse, and fundamental to those values. And the azimuthal quantum number can be 0 or any positive integer smaller than n. Okay, so n can be 1, 2, 3, 4, 5, 6, 7, 8, ... L can be 0, 1, 2, 3, ... anywhere up to n minus 1. Okay, so if n is 2, L could be 0 or 1. If n is 3, L could be 0, 1, or 2. If n equals 4, L could be 0, 1, 2, or 3. If n equals 1, L can be 0, and that's all it can be. Okay. An orbital is named by listing the numerical value for n followed by the letter that corresponds to the numerical value for L. So 3s orbital means n equals 3 and L equals 0. 5f orbital means n equals 5 and L equals 3. N equals 1, L can be 0. So a 1s orbital exists, but there's no 1p orbital because 1p orbital would be n equals 1 and L equals 1. But L, and the second order differential equations tell us this, L can't be 1 if n is 1. The highest it can be is 0. So that's not valid. 1D is not valid. 1F is not valid. After F, by the way, it goes alphabetically. And 1G is not valid. 2S and 2P are good, right? 2P subshell, or we aren't into subshells yet, just a 2p orbital, n equals 2, L equals 1, that's allowed. N equals 2, L equals 0, that's allowed. N equals 2, L equals 2, that's not allowed. 2d, 2f, 2g orbitals, those aren't allowed. Remember, n restricts L, but L does not restrict n. So 6f orbital, that's legal, that's okay. N equals 6, L equals 3. But n equals 3, L equals 6, that's no good. Okay, so there we're looking at orbitals, but we still need a bit more information. We need the orientation of those orbitals. If it's a sphere, we don't care because it's spherically symmetric. But with P, D, F, etc., you do need some more information. So you need a third quantum number called m sub L. If L is 0, then it's an s orbital and there's no preferred axis of rotation. So m sub L is 0. But if L equals 1, there can be a preferred axis of rotation, a directionality to it, and that gives us 3 possible values for m sub L. Any of the 3 directions, x, y, or z, right? In a 3-dimensional coordinate system. One way to write it is x and y in the plane, and then z going out. So if L is 1, m sub L can be 1, 0, minus 1. If L equals 2, then you can have m sub L 2, 1, 0, minus 1, minus 2. If L equals 3, then m sub L can be 3, 2, 1, 0, minus 1, minus 2, minus 3. In fact, there are 2L plus 1 m sub L values for a given L. Okay? Then, as mentioned in section 4.4, an electron has magnetism associated with it, and the magnetism is directional, so the spin of electron is directional too. Electron spin has only 2 possible orientations. Spin orientation, m sub s, can be plus 1/2 or minus 1/2. So spin up or spin down. And a complete description of atomic electron requires 4 quantum numbers, making one set. We said that before. N, L, m sub L, and m sub s. Okay. Here's a summary of the restrictions. Quantum number n, 1, 2 to infinity, L, 0, 1 to n minus 1, m sub L goes from minus L to L, m sub s minus 1/2 or plus 1/2. That's it. So, an electron in a 3p orbital, you could have n equals 3, L equals 1, m sub L equals plus 1, m sub s is plus 1/2. Or m sub L equals 0, these others being the same. Or m sub L equals minus 1, the others being the same. Or, what's the difference here? Oh, now we're just switching all the m sub s to negative 1/2. So there's 6 valid sets of quantum numbers for an electron in a 3p orbital. And we're going to learn very soon that the maximum number of electrons you can put in a 3p subshell, which is a group of 3p orbitals, is 6. 2 electrons per orbital. Okay. So let's look at some valid quantum numbers. Determine how many valid sets of quantum numbers exist for 4D. Okay, so a 4D orbital, so you're going to have quantum number 4, L equals 2, so m sub L can be 2, 1, 0, minus 1, minus 2, m sub s plus 1/2 or minus 1/2. Okay, so there's 10, right? 1 times 1 times 5 times 2, 10. 10 sets of quantum numbers. Here's one of them, 4, 2, 1 plus 1/2. Here's another one, 4, 2, minus 2, minus 1/2. And you should be able to list the other 8 sets. Go for it. Okay. Write all the valid sets of quantum numbers of the 5p. Well, 5p orbital, so n equals 5, L equals 1, m sub L can be 1 plus 1/2, Then you could have 5, 1, 0 plus 1/2, 5, 1, negative 1 plus 1/2. Then you could have 5, 1, 1 minus 1/2, 5, 1, 0 minus 1/2, 5, 1 minus 1 minus 1/2. So there are 6. You can get more practice there. And let's try the section exercise 4.52 B. Okay. Oh, no, let's do 1. Okay, list all the valid sets of quantum numbers for n equals 3. So we're going to have 3. Oh, that's a lot. 3, 2, 2 plus 1/2. 3, 2, 1, 3, 2, 0, 3, 2 minus 1, 3, 2 minus 2. And I could have plus 1/2. I could do the whole thing with minus 1/2. Okay. Then I could do, so that would take care of the 3D. Then the 3P set, so I'd have 3, 1, 1 plus 1/2, 3, 1, 0, 3, 1 minus 1. And then the whole thing with the minus 1/2. Okay. And then I could do 3, 0, 0 plus 1/2, and 3, 0, 0 minus 1/2. Okay, so there's lots. Okay, so write them all out and get some practice on it. But sometimes things aren't valid. Here you got, is this one legit? Which of the following sets describe actual orbitals which are non-existent? Well, the first one got n equals 4, L equals 1, m sub L equals, m sub s equals 0. No, it has to be plus 1/2 or minus 1/2, so that's no good. The second one, 4, 4, 1 plus 1/2. Well, those two are good. Oh, but the L's not. L has to be at least 1 less than n, so that's no good. Here, 4, 0, m sub L is 1, m sub s is plus 1/2. That's no good. M sub L can only be one value for it. 2 times 0 plus 1 is 1. One value, but that value can't be 1. It has to be 0, because m sub L ranges from minus L to plus L in steps of 1, but 0 to 0, well, it's 0. N equals 4, L equals 2, m sub L equals 2, and m sub s equals minus 1/2. Yeah, that one's good. Okay, and then you can try for practice n equals 4. Okay, so our next class, we will talk about the shapes of the quantum numbers and start putting things together and filling up electrons. We're actually going to bridge a little bit Chapter 4 and Chapter 5. Okay? Sounds good.